Dear students, in this video I will explain some algebra of limits. Here we shall discussing some important properties on a differential calculus. That is, let f of x and g of x be two functions such that limit x tends to a f of x is equal to L and limit x tends to a g of x is equal to M. Then the following properties of limits are true. That is, number 1, limit x tends to a f of x plus g of x is equal to limit x tends to a f of x plus limit x tends to a g of x is equal to L plus M is called arithmetic rule. Second one is limit x tends to a f of x minus g of x is equal to limit x tends to a f of x minus limit x tends to a g of x is equal to g of x. It implies L minus M is called subtraction rule. Limit x tends to a f of x minus g of x is equal to limit x tends to a f of x into limit x tends to a g of x. It implies L into M is called product rule. And fourth one is limit x tends to a c into f of x is equal to c into limit x tends to a f of x, where c is a constant. Fifth one is limit x tends to a f of x by g of x is equal to limit x tends to a f of x by limit x tends to a g of x is equal to L by M. If M is not equal to 0, is called quotient rule. Okay. Next, let us prove in below one by one. That is, in first, let f of x and g of x be two functions such that limit x tends to a f of x is equal to L and limit x tends to a g of x is equal to M. Then we have to prove limit x tends to a f of x plus g of x is equal to L plus M. And second one is limit x tends to a f of x minus g of x is equal to L minus M. Okay. This property have to prove by using the definition of limit of a function. That is, see, in this statement, what are the given? First you write it. That is given limit x tends to a f of x is equal to L and limit x tends to a g of x is equal to M. Okay, it implies by the definition limit x tends to a f of x is equal to L for every real number is greater than 0. There exists a very small real number delta 1 is greater than 0 such that modulus f of x minus L less than epsilon by 2 for 0 which is less than modulus x minus L less than delta 1. Write it as equation number 1. Next, it implies limit x tends to a g of x is equal to M. Here also by the definition of limit of a function for every epsilon greater than 0, there exists a very small real number delta 2 is greater than 0 such that modulus g of x minus M is less than epsilon by 2. For 0 less than modulus x minus A is less than delta 2. Write it as equation number 2. Let delta is equal to minimum of delta 1 comma delta 2. Then from equation 1 and 2 we have modulus f of x minus L which is less than epsilon by 2 and modulus g of x minus M is less than epsilon by 2 for 0 which is less than modulus x minus A less than delta. Means delta means is a minimum of delta 1 comma delta 2 you see in above. Okay. Now consider modulus f of x plus g of x minus of L plus M is equal to, see, modulus f of x, you write first term f of x minus L plus g of x minus m, which is less than or equal to modulus f of x minus L plus modulus g of x minus m, because modulus a plus b, which is less than or equal to modulus a plus modulus b. Like this, the above modulus function can be written as like this. Okay, which is less than, you see from equation 1 the first term is less than epsilon by 2, and you see from equation 2 the second term is epsilon by 2 is equal to epsilon. For 0 is less than modulus x minus a less than delta. Thus we have for every real number greater than 0, then there exists a very small real number delta is greater than 0, where 0 is less than modulus x minus a less than delta. Hence the limit of the function f of x plus g of x as x tends to a is equal to L plus m. Okay, hence its proof. Okay, hence the proof. Similarly, how to prove the second one, that is here also by using the definition of a limit of a function, that is given epsilon, that is given limit x tends to a f of x is equal to L and limit x tends to a g of x is equal to m. By the definition, limit x tends to a f of x equal to L means for every epsilon is greater than 0, there exists very small real number delta 1 is greater than 0 such that modulus f of x minus L less than epsilon by 2 for 0 less than modulus x minus L less than delta 1. That is equation number 1. And limit x tends to a g of x is equal to m for every epsilon is greater than 0, there exists delta 2 is greater than 0 such that modulus g of x minus m less than epsilon by 2 for 0 less than modulus x minus L less than delta 2. Write it as equation number 2. Let delta is equal to minimum of delta 1 comma delta 2. So then from equation 1 and 2 we have modulus f of x minus L less than epsilon by 2 and modulus g of x minus m less than epsilon by 2 for 0 is less than mod x minus a less than delta. Now consider modulus f of x minus g of x plus of L minus m is equal to modulus f of x minus g of x plus plus of minus 1 into L minus m. Okay, so on simplification we have modulus f of x minus g of x, see, minus L plus m. On further simplification we have modulus f of x minus L plus m minus g of x. So which is less than or equal to modulus f of x minus L plus modulus m minus g of x. Okay, and further which is less than or equal to modulus f of x minus L plus modulus g of x minus m, because modulus m minus g of x is less than or equal to modulus g of x minus m. Okay, next which is less than, you see from equation 1 the first term is epsilon by 2 and the second term by equation 2 epsilon by 2, that is epsilon by 2 plus epsilon by 2 is equal to what? Epsilon. Okay, for 0 which is less than mod x minus a less than delta. Thus we have for every epsilon is greater than 0, there exists a real number delta is greater than 0 such that modulus f of x minus g of x minus of L minus m is less than epsilon for 0 which is less than mod x minus a less than delta. Okay, hence limit x tends to a f of x minus g of x is equal to L minus m. Okay, or in one more for, you see, for in second property I have to prove in one more method, that is you see consider limit x tends to a f of x minus g of x is equal to limit x tends to a f of x plus minus 1 into g of x, means the LHS can also be written like this. Okay, that is equal to limit x tends to a f of x plus limit x tends to a minus 1 into g of x, or on further simplification we have limit x tends to a f of x plus minus 1 into limit as x tends to a g of x, because minus 1 is constant. So that is equal to, you see, limit extends to f of x is equal to what? L plus again plus minus 1 into m is equal to what? L minus m. Okay. Next, how to prove the third property, that is limit extends to a f of x into g of x is equal to L into m. Okay. First you write here, let limit as extends to a f of x is equal to L and limit extends to a g of x is equal to m is given. Okay. It implies limit extends to a f of x equal to L means by the definition of limit of a function where every epsilon 1 is greater than 0, then there exists a corresponding real number delta 1 is also greater than 0 such that modulus f of x minus L less than epsilon 1. For 0 which is less than modulus x minus L less than delta 1. Write it as equation number 1. Or it implies limit extends to a g of x is equal to m. Here also by the definition of limit of a function where every epsilon 1 is greater than 0, then there exists a corresponding real number delta 2 is greater than 0 such that modulus g of x minus m is less than epsilon 1. For 0 less than modulus x minus l less than delta 2, write it as equation number 2. And let delta is a minimum of delta 1 comma delta 2. Then from equation 1 and 2 we have modulus f of x minus L less than epsilon 1 and modulus g of x minus m which is less than epsilon 1. For 0 which is less than modulus x minus L less than delta. Write it as equation number 3. Now we have modulus g of x is equal to, it can be split as g of x minus m plus m. So that is less than or equal to modulus g of x minus m plus modulus m. So less than or equal to, you see from equation 2, so the first term is less than epsilon 1 plus modulus m. For 0 less than modulus x minus L delta. Now consider modulus g f of x into g of x minus into L into m is equal to, it can be split as f of x into g of x minus L into g of x plus L into g of x minus L into m. And simplification here we have, you see, modulus f of x, here modulus g of x is take comma, then g of x of f of x minus L plus L of g of x minus m which is less than or equal to modulus g of x into modulus f of x minus L plus by modulus property. Okay, modulus L into modulus g of x minus m. So less than, see, where modulus g of x means what? 1 plus modulus m into modulus f of x minus L means epsilon 1 plus again modulus L into again g of x minus m means epsilon 1 for 0 less than x minus L less than delta. Since using equation 1 and 2, now we have choose epsilon 1 is equal to epsilon by modulus L plus modulus m plus 1, where epsilon is a very small number, then okay, hence modulus f of x into g of x minus L into m which is less than epsilon. For 0 is less than modulus x minus L less than delta. This implies that limit extends to a f of x into g of x is equal to L plus m. Okay. The fourth property is limit extends to a c into f of x is equal to c into limit extends to a f of x, where c is a constant. Here let epsilon is a very small number is greater than 0. Then because limit extends to f of x is equal to L, by the definition of the limit there is a one more corresponding real number delta 1 is greater than 0 means positive, such that modulus f of x minus a which less than epsilon by modulus c. Whenever 0 which less than mod x minus a less than delta 1. Now we choose delta 1 is equal to delta, and we need to show that modulus c into f of x minus c into L which is less than epsilon. Whenever 0 less than modulus x minus c less than delta, and then modulus of modulus c into f of x minus c into L is equal to modulus C into modulus f of x minus L, which is less than modulus C means constant C into epsilon by modulus C. So after simplification we have epsilon, and hence limit as x tend to a C into f of x is equal to C into limit x tend to f of x. Okay. Next we go the next property, that is limit x tend to a f of x by g of x is equal to limit x tend to a f of x by limit x tend to a g of x is equal to L by M, where M is non-zero, not equal to 0. Before we go into this, we first show that limit as x tend to 1 by g of x is equal to 1 by M. Okay. Now limit x tend to a g of x is equal to M by the definition of limit of the function for every epsilon 1 greater than 0, then there exists a corresponding real number greater than 0, delta 1 is greater than 0, such that modulus g of x minus m is less than epsilon 1. For 0 is less than modulus x minus less than delta 1. Now consider modulus m is equal to modulus m minus g of x plus g of x. Okay, which is less than or equal to modulus m minus g of x plus modulus g of x, and further which is less than or equal to modulus g of x minus m plus modulus g of x, which is less than, see, modulus g of x minus m means what is less than epsilon 1 plus modulus g of x. For 0 less than modulus x minus a less than delta 1. Therefore g of x is greater than modulus m, you see, modulus m minus epsilon 1, where 0 less than modulus x minus a less than delta 1. Okay, let us choose where epsilon 1 is equal to modulus m by 2. Then we have the above expression will becomes g of x is greater than m minus where epsilon 1 is modulus m by 2. On simplification we have g of x is greater than modulus m by 2. For 0 is less than modulus x minus a less than delta 1. So that is 1 by g of x which is less than 2 by modulus m. For 0 which is less than modulus x minus a less than delta 1. And again as limit x tend to a g of x is equal to m for every epsilon 2 greater than 0, then there exists a real number delta 2 greater than 0 such that so 0 for 0 is less than modulus x minus a less than delta 2, that is let delta is equal to minimum of delta 1 comma delta 2, then 1 by g of x which is less than 2 by modulus m for 0 less than modulus x minus a less than delta, that is equation number 1. And modulus g of x minus m which is less than epsilon 1 for 0 is less than modulus x minus a less than delta, so write it as equation number 2. Now consider modulus 1 by g of x into 1 by m, 1 by modulus m is equal to 1 by g of x minus 1 by modulus m is equal to, here on simplification we have its LCM is m into g of x, so the numerator is minus g of x by m into g of x, which is less than or equal to modulus m minus g of x by modulus m into modulus g of x. On further simplification we have which is less than or equal to modulus m g of x minus m by modulus m into modulus g of x, which is less than where modulus is g of x minus m means see 1 by g of x is equal to, you see in above that is equation 1, 1 by g of x means epsilon 2 by modulus m. Okay, and again so g of x means epsilon 2 by modulus m. Okay, since from equation 1 and 2. Okay, now we choose epsilon 2 which is less than modulus m whole square by 2 into epsilon, where epsilon is given positive number however small. Okay, therefore the above equation will become, that is modulus 1 by g of x minus 1 by m which is less than epsilon 1. Okay, for 0 less than modulus x minus a less than delta, hence limit x tends to a 1 by g of x is equal to 1 by m by m. Now consider limit x tends to a f of x by g of x is equal to limit x tends to a f of x into 1 by g of x. Okay, that is equal to limit x tends to a f of x into limit x tends to a 1 by g of x. That is equal to where limit x tends to a f of x is L into limit x tends to a 1 by g of x is 1 by m. That is equal to L by m. Hence, limit x tends to a f of x by g of x is equal to L by m. Okay.